Hey, this is OXDF, and today we're looking at the 9th challenge in this year's FlareOn event. It's a challenge called Encryptor, and it's meant to simulate some real-life ransomware. Now, they put some protections in place so that it doesn't encrypt all the players' drives or etc., but the overall approach it takes is actually relatively realistic. And it's worth just a quick second to talk about ransomware and symmetric key encryption versus asymmetric key encryption. In symmetric key encryption, you use one key to encrypt and decrypt, and it's very fast. It can go across, you can either stream or block, can go across large amounts of data very quickly. Asymmetric encryption, typically you have a public key and a private key, and if you use the public key to encrypt something, then only someone who has the private key can decrypt it. And so the advantage from a ransomware point of view is if I do that, I can hold the private key on my box, send the public key with the malware, encrypt stuff with it, and then only people who have the private key, me, can decrypt it, or I guess people who pay for it, right? The problem with asymmetric encryption is it's really slow. It takes a long time. So if you're trying to encrypt a whole computer, it's gonna take a long time. So the hybrid that you see out in the wild a lot is to have malware generate a random key and use symmetric encryption to encrypt a bunch of stuff. Then use asymmetric encryption to encrypt that key and attach it to the file. And now, if someone wants to decrypt that file, they need to decrypt the key. Well, to decrypt the key, they still need the private key that I'm holding, back in my layer. So that's a pretty common pattern that you'll see in ransomware. The mistake they use in this ransomware, and I'm not going to do too much of the reverse engineering in this video, actually. If you want to see how all of that comes about, check out the full blog post. There'll be a link in the description. But the mistake they make is they use the private key to encrypt. And so now if I have the public key, which I do, it's in the malware as well, I can, and N, which is the other half of that, I can decrypt the key and go ahead and get the plaintext back, right? So let's first take a look at, let's see, I'm gonna actually split this screen here. Let's first take a look at a test file that I encrypted using the malware. And basically, via the reverse engineering that, again, I'll go through in detail in the blog post, you can see this right here is actually the stream cipher encrypted version of it's my input encrypted with a stream cipher. And then there's these 4 blocks. So 1, 2, 3, 4, all with a new line on the end of hex data, and they represent different things. What I happen to know is, again, via the reverse engineering, that one of these, so let's see, this one right here, I believe, is the N value, and there's another one of these, right, which is the last one right here, is the encrypted key and nonce used in ChaCha20. So what I want to be able to do then is pull this N value out as well as the encrypted key, decrypt the key, and then use that to decrypt this stuff right up at the front. And so we're going to write a quick Python script to do that. Let's scoot this over a little bit so we can keep it on our view, but that we can work here. So we'll do vim decrypt.py. We'll always start with our shebang. Oops, python. Man, typing is hard. Python 3. We will import sys. And we're going to go ahead and we'll just do from crypto.cipher import ChaCha20. All right, so first thing we're going to do is we'll open up the file here. So we'll do with open sys.argv, and I always just like to do, let my scripts read different files this way. That way I can practice, for example, on this file, and then I should say the challenge actually came with another file that looks very similar called suspicious text file encrypted. So same format, and presumably I'm going to say the flag is going to be in this decrypted stuff right here. So let's see, we can close that. Let's open up the other one just because we'll start working on the test file because we know what's in the test file. You don't actually, I realize, but we could do vim and we call it test.encryptme, and there it is. This is a test file. So that gives us some idea of what we're aiming for as we try to do that. So we will open up the file and we will just call, what do we call this? Enc file equals f.read. Works for me. So now the first thing we need to do is we need to split and get these values out. And we've already said the ciphertext is right here at the front. Then we have N right here as sort of the first one after the first new line, and then the key and nonce come here at the end. So what I'm going to use here is I'll say values equals, and we'll say inc file dot rsplit. Now what rsplit lets me do is split from the reverse split. So split, I guess I'll start here. I could start with just a split on new line like that, and I would get this 2, 3, 4, and then an empty one at the end. And that's going to work at least in my test file case. But what I can't guarantee is that any of this encrypted data won't ever become a new line. And as soon as it does, then all of my potential breaks afterwards don't make any sense. So instead, I could like reverse the whole thing and then do a split n, because split n then say like only split 4 times, right? So that would give me the nothing at the end, and then this 1, 2, 3, and then this last bit, all of this, including any new lines in here, it wouldn't be split on. But I'm actually, instead of using split n, I'm going to use rsplit, and that's going to start splitting at the back. So it's going to take the last 4 splits possible. In fact, we can run this. Let's see. If we do python -i decrypt, and we call it test.encrypted, f is not defined. It's helpful if I add that as, yeah. Bytes like object is okay. So because inc file is bytes and not string, I need to split on bytes and not a string. There we go. All right, so we have values, and we can see if we zoom in on here that values sub 0 is the encrypted stuff with the first one of these. There's our n and value sub 1. Value sub 4 is the empty one at the end because it ends in a new line, so there's technically an empty string after it. And so value sub 3 is going to be our encrypted nonce and key. So we will come in here and we will start to split this. So we'll say like encrypted key nonce equals values dot 3. And in fact, what we really want to do is turn this into an integer. We'll turn and say int. Actually, do we want to turn this into an integer? Yeah, because it's encrypted. We need to turn this into an integer because we're going to RSA decrypt, and when you have RSA, you just want to work with integers. So we'll turn this into an integer like that. We can say n, which is also an integer, is going to be values sub 1, 16. And so when I pass this into int, basically what I'm doing is I'm saying, give me this buffer of hex and convert it to an integer at base 16. So that'll work. And then I need to get my ciphertext. And so that's going to be values sub 0. And what I really want is, I know this stuff at the end is always going to be the same size. And I know it's going to be 256 bytes or 128. If the hex will convert to 128, so it's 256 bytes. So I can do something like this where I do minus 256. This will say read from the beginning up through 256 from the end. So that'll give me my ciphertext. So now I have that, I need to go ahead and do the RSA. And so I can do plaintext key nonce, like what I'm going to get out of this. And RSA is really actually quite simple. All you're going to do is take a power of the encrypted stuff, so the ciphertext, so we'll say enc key nonce raised to the private key, or in this case, the public key because they screwed up. And so we know that's 0x1001, the default public key. And then mod your n. And so Python, if you do pow with just 2 arguments, it's this one to this one, but if you add a third one, it's mod this. So, and that's it. That'll give us the key. One thing we can do after this is we can say that'll give us an integer, which is our plain text, right? But we really want this as bytes. So we'll say 2 bytes. And we know it's going to be 48 bytes. So it's going to be 32 plus 4 plus C is going to give us 48. Again, I go over how we get to that number in the blog post, and we'll add that there. Now we can say ChaCha key is equal to plaintext key nonce, the first 32 bytes, and we can say ChaCha nonce equals pt key nonce, and we want the last 12 bytes, and we've got those there. And we can stop and take a look and see how we feel about those. I say ChaCha key. Now, what I could do, and I actually did a lot while solving this problem, is at this point go through and actually make sure this matches up nicely with the key when I see it generated. But for now, again, just because we're just showing off kind of this how we made the script, we won't worry about it. We'll take on faith that that's going to work. So now we can say ChaCha equals, and we'll say ChaCha20 2020.new, and you got to pass in a key equals ChaCha key, and a nonce is equal to ChaCha nonce, and that's it. And now we can just say plaintext equals ChaCha.decrypt ciphertext, and we can print pt.decode. And if that works, we'll see if we can get it on the first try. We should see our result, and we see this is a test file. So we've managed to write some real simple Python that decodes this for us. We can get rid of the -i because we're not using that anymore, and instead of this we can say suspicious file, and we get hello, the flag is, and then there's our RSA. I don't know exactly what this says. Something RSA something is opposite of encryption. So yeah. Cool. Hopefully this was useful. Just another quick little Python video. Again, this is a really interesting challenge. I recommend you check out the whole blog quiz for all the details, but I'm going to go ahead and call this video here. Thanks so much for sticking around to the end, and I'll talk to you next time.